would like to introduce Sarah Chen, who is a software engineer at Arista. She will be presenting on dynamic flooding in Supernodes.
Thank you, Tom. I will present to you today dynamic flooding in Supernodes. In this presentation, I will first introduce the supernode architecture. I will show you how supernodes can be built as alternatives to core routers. And the supernodes run link state IGP and can benefit TE, SR, and BER. However, link state IGP has a flooding problem in the dense topologies. And in this talk, I will present our solution called dynamic flooding to this problem. So what do we need to do? What do we need to build a core router anyway? First, we need a fabric, which provides the bandwidth. Then we need the CPU for control and management. And we also need the line cards for interfaces and packet forwarding. So let's think about, what if the fabric is just Ethernet? What if the control and management plane was distributed? And what if the line cards are small fixed form factor routers? Then it becomes our supernodes. So here to start with, the fabric becomes dual spines, a pair of spine nodes, and the line cards become small routers. The small routers are connected to the spine in a leaf spine topology. You can actually choose any topology for redundancy, but to start with, we assume that they can be connected to the leaf spine topology. So in this, then it becomes our supernode. So it can be extended very easily. You can have more leaves connecting to the spine, or you can have small spines, or even more stages. So what do we get out of from supernode? So on the left side is a legacy architecture. We see that everything is connected to two huge multi-chassis cores. And these cores are very expensive. And they are vendor locked. If you buy chassis from one vendor, then you have to buy the line cards from the same vendor. And the entire site is limited by the maximum scale of the one core router. And the software upgrade is a nightmare. So if you are lucky losing two cores, then the entire site is gone. On the other hand, if we have a supernode to replace a core node, then we can see that first it can be expanded very easily. You can have more leaves or more spines or more stages. And then it's multi-vendor. So you can buy leaves and spines from different vendors. And the software upgrade is much easier. So you can upgrade one node at a time incrementally. So in the large, we can build the internet using the supernodes. So on the right-hand side, the picture shows a 6-node internet. So every node is actually a supernode consisting of 2 spines and 8 leaves. So a total of 60 nodes. So if we scale up to some production number, then the IGP scale may be a problem. So on top of the to-do list for supernode is the scalable routing within the supernode. We want to use link state IGP within the supernode. However, link state flooding has a problem in the dense topology. I will explain this later. And we need some improvement here. And on this list, we also list another two items, the control plane abstraction and architecture scalability. I will not cover this in this talk. We have separate drafts for these two items. If you are interested, you can check that. This slide tries to convince you that link state is a good idea. So information regarding the behavior and the characteristic state of links in the network is easily conveyed in IGP. And our next generation multicast and the traffic engineer can all benefit from link state IGP. However, the IGP has a scaling limit, which is caused by the flooding. So IGP flooding is optimistic and complete. So if a node receives an update from one neighbor, then it will flood this update to all its other neighbors. So in a dense topology, the amount of information flooded may overwhelm the control plane at scale. So maybe there's one node cannot catch up, so it will lose the hello packets and drop the adjacencies. This will cause more link state updates and causing another wave of flooding. Then in a big dense network, there are maybe multiple nodes who are overwhelmed. At the end, this can cause a network collapse. So our goal is to reduce the flooding in a dense topology. So the idea is we select a subgraph of the physical topology. And then the link state updates are only flooded on this subgraph. We call it flooding topology. And we can choose the sparse subgraph to reduce the flooding in the network. So here's an example. So on the left, we have the link states updates are flooded on every link. But on the right-hand side, we have a flooding topology, which is a subset of the original physical topology. So ideally, every node will only receive one copy of the link state update. So we call our solution as dynamic flooding. The key of dynamic flooding is to choose the flooding topology from the physical topology. So here list the 5 requirements for that. First, the flooding topology has to cover all the nodes in the network because every node has to receive a copy of the link state update. And this flooding topology has to compute it dynamically. If a topology changes, the flooding topology has to be adaptive to the change. The second requirement is the convergence. So as mentioned before, in a dense network at a scale, we may see network collapse due to the extensive flooding. So we definitely want to do better than that. So the flooding topology has to be sparse enough. The third requirement is that the solution should address a variety of dense topologies. It should not just address a complete leaf-spine topology. That's not sufficient because when the topology changes, it no longer becomes a leaf-spine topology. So we have to deal with different kinds of dense topologies. And the multi-stage cross topologies and its variants should also be addressed. So a complete graph might not be a practical one, but addressing that is a good demonstration of the generality. The fourth requirement of the flooding topology is that there's no single point of failure. This means that if any link or any node fails, the flooding topology remains connected. So the link state updates can still reach every node. This will not cause the convergence. The fifth requirement is it should be operationally efficiency, not depending on the density of the topology. So we have an algorithm to compute the flooding topology from any dense graph. I will not cover in this topic in this presentation, but we have an IETF draft explaining this algorithm. So in this presentation, I will mainly talk about at a high level how to deploy it. So to deploy dynamic flooding, we take an centralized approach. So first, we select an area leader in the area. So we can use the DR election mechanism to elect the area leader. So the responsibility of this area leader is to compute the flooding topology from the physical topology for the entire area. So this flooding topology is then encoded into LSPs and distributed as part of the normal link state database. So every node in this area will receive the flooding topology. And once having the flooding topology, it will only flood the link states on the flooding topology. So by the way, the data traffic is still flow on the physical topology. So this flooding topology is only for the link state updates. So when there's a topology change, the area leader can recompute the flooding topology and then redistribute it. Meanwhile, the node can detect such scenario and request the temporary flooding from its neighbors. We also have a mechanism for temporary flooding. So we have extended the ISIS and the OSPF protocols to do the dynamic flooding. In particular, we added the area leader sub-TLV, basically indicates whether a system is willing to be an area leader or not. So this will be used in area leader election. And then we introduce a dynamic flooding sub-TLV. This indicates whether a node supports dynamic flooding or not. This might be useful in the distributed mode and to specify which algorithms the dynamic flooding supports. And then we have area node ID TLVs. So the area leader will assign the area node IDs to every node in the network. And then this area node IDs will be used to encode the flooding topology and then send in the flooding path TLV. And in the previous slides, I mentioned there's a temporary flooding mechanism, and this is achieved by using the flooding request TLV. So basically, a node can send the flooding request to its neighbor, and its neighbor will start flooding on this link temporarily, even if the link is not part of the flooding topology. Here, next I'm gonna show you some results from our simulation. So here, it shows a complete graph of 10 nodes. So 10 nodes are fully meshed, a total of 45 links. The solid lines are the flooding topology. The solid, including the black and the purple ones. So these are the flooding topology. You can see that it's a really sparse subgraph of the original graph. And the dashed lines are the non-flooding data links. So data flows on still flows on all the 45 links, but the link state updates only flow on the solid lines. There's only 11 flooding links on it. Here's the flooding topology for 4 spine and 17 leaves. So those are connected in a leaf spine topology. You can see that every leaf is connecting to all the spines. So this can be replace the core router in a small data center or media-sized core router. Again, the solid lines are the flooding topology, and you can see that from the leaf side, you can see that originally there are 4 links, but we only choose 2 of them for flooding the link states. And on the spine side, we can also see a significantly reduced number of links to flood. Okay, this one shows 3-tiered cross topology with 16 spines and 16, 64, 108 in each tiers. And this can be a large core router replacement. We didn't put those non-flooding data links, otherwise you can just see all black. But this is the flooding topology for this. Okay, this is a flooding topology for 4 spines and 60 leaves. So each leaf is connecting to all the spines, and only two links are chosen as the as in the flooding topology. So here are some numerical results. So we boot up a leaf spine topology with 4 spines and 60 leaves, and we count the LSPs and the IIHs during the process. And we find that without dynamic flooding, the spine has to process 110,000 LSP and IIHs, and the leaves had to process 15,000. But with dynamic flooding, we can see a significantly reduced number. There's a 62% saving in spines and 77% saving in leaves, a saving of flooding. So in summary, dynamic flooding can dramatically reduce the number of links used for flooding in the dense physical topology. So the decreased flooding allows the control plane to scale. So we can build a much larger and dense topology running IGP, link state IGPs. And using such large topologies, we can build supernodes to replace the legacy core routers. And the benefits of supernodes are listed here. So it's a multi-vendor. It's mix and match chassis. You can buy what you need and when you need it. It expands very easily. It grows as you need. You can buy more leaves, or you can expand by adding more spines or adding more tiers. And the software upgrade is much easier. Instead of having a single chassis upgrade, you just incrementally upgrade the routers one by one. That's cost less disruptive. And in the legacy architecture, if both core routers are lost, then the entire site is lost. So with the supernode architecture, the chances of losing the entire supernode is very minimal. Okay, that's it for my presentation. Thank you.
And for our questions, please make sure to use the questions panel to ask any questions for the speaker. Our first question is Arista considering implementing Rift?
Not now. We don't have any plan for that.
Okay, short and sweet. Another question is the solution for within a data center? Why would you need IGP within a data center fabric when we can use BGP route vector instead? Do people do RSVP-TE or RSTE within a data center fabric?
Yes, it can. We can use it in the data center. So because our algorithm don't count on the topology, so you can use in any scenario. So in the data center scenario, you can use it for the pod. So we have error abstraction, which is not covered in this talk. So you can abstract the whole pod, the data center pod, as an area. So as a supernode.
Okay. Could you explain a bit about the advantages of using LS routing protocols to manage data center compared with using path vector routing, aka BGP?
So I think I have a slide for the why use link state. And so currently we use BGP, but we have a lot of hacks to the natural BGP to carry the link states, the various link states. So if we use the link state protocol, which is already carrying those information, then we have all those TE and like next generation beer, all those benefits coming.
Okay. I just want to send a quick reminder that right after this, there's going to be a newcomers Zoom session with breakouts. And again, if you have any more questions, please submit them to the questions queue. I guess there's a request to see more results on of simulations, example, convergence performance, reduction LFA, convergence, less optimal, best path calculation in a bigger deck. Is that something that you potentially have somewhere online or could publish?
So we have a lot of simulations basically to test the algorithm and to compute the flooding topology. But I don't want to mention that the flooding topology is mainly to flood the link states. It's not used for the data traffic. So the data traffic still flows on the physical topology. We have simulations for the algorithm, but we haven't deployed it in a large network to get simulation results for the convergence yet. But we have simulation results, not the real.
Okay. I guess one last final reminder, after this presentation, we're going to take a 1 hour break. During that 1 hour, if you're interested, there's a newcomers Zoom with breakout different sessions. And outside of that, thank you very much.
Thank you.